Alright, in today's video we're going to talk about the solubility product constant, the KSP. It's just another equilibrium constant, but the little lowercase sp reminds you you're talking about slightly soluble, or what we often call insoluble salts, but we've learned in equilibrium that they're actually slightly soluble. So let's take one of these salts, lead chloride, and if you were to throw some lead chloride into water, for example, it predominantly would stay together. It would be solid lead chloride in some sort of ionic lattice where the positive lead 2 ions are connected to the chloride minus ions. And these tend to be insoluble because they're highly charged and compact, and you can't get enough waters around them. The polar waters have to surround them and start to break them apart. So it's an insoluble salt, and this is quite common with highly charged metals or anions that are -2 and above. So if we were trying to figure out the equilibrium for this, we'd set up an equilibrium expression which leaves the lead chloride solid out of the expression. And basically you would say KSP equals lead 2 and chloride in solution. I just want you to understand, look, I see a K, it's 1.17 times 10 to the minus 5. That's a very low K. So just a few of these little lead chlorides will kind of disassociate. The rest of them will stay clumped together and insoluble. So our goal is to figure out exactly how much lead dissolves. That's why we call it the solubility product constant. And one thing I'd point out is that the number of lead 2 pluses that dissolved are stoichiometrically related to the number of lead chloride salts that disassociated. So in essence, if I could tell you that lead 2 plus is 4 molar, then that would mean that 4 moles of lead 2 chloride dissolved in a liter of water. So just kind of wrap your head around that the metal cation is 1-to-1 with the amount of salt that dissolved. And that's again why we call it the KSP. So if we did an ice table, what I would have you do is start with the initial conditions. There's just a boatload of the salt, the insoluble solid. Prior to any kind of change, you assume that there's no lead ions or chloride ions present. Now the change is some of that lead 2 chloride starts to dissolve, minus X, which means that plus X of the lead ions show up and plus 2X of the chloride ions show up. So at equilibrium, you would have Y minus X for the lead 2 chloride solid, but that's insignificant because it's not part of the equilibrium expression. But over on the other side, you'd have plus X for the lead 2 cations and plus 2X for the chloride ions. And then you could just plug and chug and solve it algebraically. So you set your KSB equal to X times 2X raised to the power 2. And when you clean that up, this is what I want you to also kind of lock on. Anytime you have a metal that dissolves in a 1-to-2 ratio and you work the ice table, you're always going to end up here. If it's 1-to-2 metal to anion, you're going to have KSP equals 4X cubed and solve for X. Okay? Solve for X is 1.43 times 10 to the minus 2. The units on that are in molarity, right? Once again, because it's 1-to-1 back with the original lead 2 chloride salt, that is actually the solubility of the lead 2 chloride. So you can basically say, 1.43 times 10 to the minus 2 moles of lead 2 chloride can dissolve in a liter of water at these temperature conditions. And that's a lock. At those temperature conditions, that'll always dissolve only that much lead 2 chloride. If you want, and this is only relevant to insoluble salts, if you want to express it more in terms of grams per mil, so you can think of how soluble lead 2 chloride is in water, you could start off with your molar solubility, okay? And you multiply it by the molar mass of lead 2 chloride, and it'll tell you that 3.98 grams would dissolve in a liter of water. Or if you want, you could break it down further and say 3.98 grams per 1,000 mils, divide that out, and basically have 0.00398 grams per mil. So however you want to break it apart, you now have what's called the molar solubility and also the solubility in grams per mil, which is often how you think about dissolving a material in so many mils of water. Here's something different. It's iron 2 hydroxide. It is, again, a 1 to 2, so you know the pattern that's going to fall in. Okay, do your ice table. Nothing really changes. You basically set up in KSP equals 4x to the raised to the third power, sulfur X. And there you go. There's your molar solubility of iron 2 ions, which is related back here 1 to 1 with the amount of iron 2 hydroxide that can dissolve in the water. Okay? And if you want to reinterpret it, iron 2 hydroxide is 6,000 times less soluble than lead 2 chloride. And you can see that immediately as long as the metal to anion ratio is the same. You can compare KSPs directly, and when you see this lower KSP, you know that it is less soluble. What about the solubility when the metal to anion ratio is different? You can basically set up again, same kind of idea. Set up your K. You know it's going to, the K expression is equal to the KSP. You set up your ice table. You walk your way through. All right. In this case, KSP equals x squared. And once again, that's a pattern you can use for any insoluble salt that dissolves 1 to 1 in terms of metal to anion ratio. It's always going to be set equal to x squared. So you can imagine a pattern evolving here that basically I'm going to learn if it's 1 to 1, it's going to be x squared. If it's 1 to 2, it's going to be 4x cubed, and on and on and on. Okay? Sulfur X. Set molarity. So now you can say, well, that's the moles of silver bromide solid that will actually dissolve in a liter of water at these temperature conditions. But once again, the KSP, just working off the KSP number alone, would not be okay to compare back to the KSP of like the iron hydroxide because they're in different ratios. But once you solve for the molar solubility, that will directly compare. And so obviously the lower molar solubility is actually going to be less soluble. So as I say in the notes here, if the salt ratio is not the same, you can't use KSP to get a qualitative approximation, but you can solve for molar solubility and then tell which one's more or less soluble, which is the direct number you're looking for. Okay, so now let's have you practice. Solve for the solubility of barium carbonate, which has a KSP of 2.58 times 10 to the minus 9. And when you solve both the molar solubility and in grams per liter. So at this point, you're going to want to stop the video, pause it, try and solve the problem, and when you have a solution or both solutions, then restart the video and check your work. Okay, let's see how you did. So barium carbonate, again, you can kind of look at the equilibrium here. That helps set up your KSP expression, which basically will be equal to the 2.58 times 10 to the minus 9th. Set up your ice table. And once again, you don't have to set up the ice table every time, because before long you'll get used to looking at things that go apart into one metal to one ion relationships and know it's going to be KSP equals x squared. And that'll just be a lot quicker, but until you get used to that, and I do recommend you get there at some point, you can work your ice table, solve. X equals 5.08 times 10 to the minus 5, which actually is the molar solubility of barium ions, which is consequently how much barium carbonate had to dissolve in order to make the barium ions, which is the molar solubility. Okay? And then if you change it back out to grams per liter, you could just multiply by the molar mass, and there you have it in grams per liters. So once again, you're going to find the molar mass barium carbonate by using your periodic table. Okay, so let's look at some other applications, some extended applications of solubility. Common ion effect is something that can make slightly soluble salts even less soluble. And in order to understand it, I always recommend drawing your equation and thinking about the Chatelier's principle. So for example, if I have lead chloride and it's dissolving into lead and chloride ions, the presence of chloride ions would push this equilibrium to the left, right? So if I added sodium chloride, it's going to move this towards reactants. Now, one thing that students sometimes get confused about is they go, well, wait, this is sodium chloride, this is chloride ions. Well, keep in mind, this is the net ionic equation. It just focuses on the ions of importance. And whenever you drop a salt in water, you need to consider, first off, if it's soluble, which sodium chloride is, then it will totally be adding chloride ions and sodium ions. And since sodium isn't part of this equilibrium, you can consider it to be a spectator ion. But it's a little improbable that you could add chloride ions without having the metal counter ion. So I try and kind of write it the way it is. So here's another application. Let's say that you add an acid or you add a base, okay? It's possible that that can do acid-base chemistry with one of your products and change the equilibrium. So here's an example. Barium carbonate dissolves into some barium and some carbonate ions. But if I added an acid to this, it would actually start to interact and neutralize this conjugate base. And in particular with carbonates and bicarbonates and sulfide ions, it'll actually turn them into gas, so they'll literally come out of equilibrium and be removed completely from the solution. So that'll drive the reaction hard to the right. So I've got that comment in here. Acid would remove the carbonate product. Removing the product would shift this to the right. That would make the salt more soluble. So now we're going to do an actual calculation and see how this changes things. So now we're going to do the solubility of lead 2 chloride, which we've already figured out is 1.43 times 10 to the minus 2 molar, which means that there's that many moles in a liter of the solution. How would that change if you actually were trying to dissolve the lead 2 chloride in a 0.5 molar sodium chloride solution? So you can look at the equilibrium and see that by already having chloride ions present, you actually have a common ion that's already in the reaction. So when you set up your table, it's going to change a little bit in your initial conditions. This is saturated, this is 0, but now you add the common ion in already in the initial condition. Then you go through the change, do the same sort of approach, plus 2x. Then when you're down to equilibrium, right, now it's 0.5 plus 2x. Set up your KSP, you go to solve, plug in from out of your ice table. Now at this point it's about to get complicated because you're going to set up a quadratic equation, and you can do that. But we've learned in class that, look, sometimes the amount that something changes is insignificant depending on two things. First off, it depends on how big your KSP is, which this is very small, and then how large your concentration is. And if you'll divide this concentration by this KSP, you'll see that you basically break the 400 rule, and it's okay to use it in approximation. And so now the amount of change is really insignificant. So you can just solve as is without doing the plus 2x. Makes my math fairly simple. But remember, the 0.5 is still squared. Okay? When you get done, you solve. X is actually 4.68 times 10 to the minus 5th. And X actually, in this case, equals the lead 2 ions, which is directly related to the lead 2 chloride. So I would recommend on this particular problem, plug your X back in along with your 0.5 and solve and see if it does indeed equal the equilibrium constant. Okay, what about acid-base influencing solubility? If the solubility of barium carbonate, which we figured out earlier, is 5.08 times 10 to the minus 5 moles per liter, then what is the solubility when you drop that same barium carbonate inside a 0.01 molar HCl solution? So again, we set up our equilibrium, but in this case we got something unique going on, because really when you have barium carbonate in HCl and you react it, you actually create carbon dioxide gas, which drives, because carbon dioxide gas is leaving, right, it's actually driving the equilibrium to the right. And this is actually this is a very high K, this is very favorable reaction. So you can kind of consider that in the presence of an acid, it starts to remove the carbonate. And in fact, it's kind of interesting to see that the moles of HCl, right, are in a 2-to-1 ratio without how much barium is formed. So that's important to keep in mind. Now we go set up our table. Now something's changed, because here's what happened. The minute the HCl was present, it created all these barium ions according to how much HCl was put in. So the initial condition here is actually half of this 0.01 molar HCl, because it's 2-to-1 with this, according to the stoichiometry. You look at the change, you find the equilibrium amount, and then you set it up in your equilibrium expression as you've learned so far. Now once again you kind of have another interesting situation. I'm starting off with 0.005 molar barium already in solution. Okay? The amount that the X adds to it whenever it disassociates in this condition, and we've already added some of this to it, and it has a very unfavorable equilibrium constant to begin with, that's really going to be insignificant. Okay, so I can actually take that out again, which makes my calculations very easy. Solve for X. And now I have that X is 5.16 times 10 to the minus 7. I always go back and see where is the X in here. Oh, that's actually the carbonate that I solved for. And just so long as the carbonate is 1-to-1 with the barium carbonate, I literally would have the answer, but that's not actually the solubility, because the truth of the matter is it's 0.005 plus X is how much barium really got dissolved, right? And that's how much of this got dissolved. But that little amount, that 5.16 times 10 to the minus 7 that's added on to the 0.005 is insignificant. Long story short, the acid control that totally controlled the solubility of the barium carbonate. So you need to work through this a few times, but basically the acid controlled the solubility of the barium carbonate. The acid is actually 2-to-1 with the barium ions, right? Which really is the solubility of the barium carbonate. Check your work. So basically now I do need to have that a little bit of amount that the barium carbonate that would show up. I need to plug it in, or else I'd be plugging in a 0. I take that number, the 5.16 times 10 to the minus 7, that's from the carbonate. I take in the original acid amount, and I don't need to add on the insignificant 5.16 times 10 to the minus 7. I multiply it together, and I get 2.58 times 10 to the minus 9, which is the KSP, so this checks out. So here's 3 problems for you to practice. Number 1, solve for the molar solubility in grams per mil. Now keep in mind we've been doing grams per liter, so adjust to milliliters. Do that for the solubility of magnesium hydroxide, which is also commonly called milk of magnesia. It's a very insoluble hydroxide. Then I want you to do the same calculation when the pH is 2 due to HCl being in the solution. So the third calculation is where you're going to do the common ion effect, where you have that magnesium already in place. So at this point, stop the video, try and solve these problems. When you think you have good answers, restart the video and check your work. Okay, let's see how you did. Number 1, let's solve for the molar solubility in grams per mil solubility of magnesium hydroxide. Okay, so once again, you're going to get used to seeing, hey, this is a 1 to 2 metal ion. You don't always have to build the ice table. It's going to be 4x cubed equals KSP. Solve for x. And keep in mind, you want to double check that x is 1 to 1 with the original material. So that is actually the molar solubility of the magnesium hydroxide. It's one answer. You could rewrite that its molar solubility is how many moles there are in 1,000 mils. It's redefining what molarity means. Take the molecular weight. Moles cancel. You're left with grams per mil. And it's 2.16 times 10 to the minus 7 grams per mil. And there's your second answer. Okay, let's move on to problem number 2. Now we're doing the same thing, only now we have an acid present. But we got to think about how many protons are in there when we know that it's pH 2. And so we've been learning in class that if you want make the pH negative, raise it to the power of 10, you'll basically be back to the concentration of the H plus ions. So now I'm going to set up the equilibrium just so I can study it. It's magnesium hydroxide becoming slightly soluble. Now this is going to be important because some of you in class have been looking at whenever you drop a weak acid that's in the form of an insoluble hydroxide, how acidic or basic it makes the water. And this KSP is the solution to that. It shows you, if you solve for this, it would solve for how many hydroxide ions, and then you'd be off where you could work your way around the block and figure the POH, the pH, and the H plus concentration. But anyway, for this problem, it's a little different because now we're going to have an acid that attacks this hydroxide and shifts the equilibrium. And I'm going to set this up a little different just to show you that basically if you want, because we learned earlier that really the amount of acid is actually directly related to the amount of the insoluble salt that dissolves. And according to this stoichiometry, the amount of acid, which we figured is right here, it's in a 1-to-1 ratio. That's a neutralization. Whenever you neutralize an acid with a base, it's always 1-to-1 like this. According to the equilibrium, for every 2 hydroxides, right here, there's 1 magnesium. So that would tell you that if based on the hydroxides present, here's the neutralization, there'll be 1 magnesium dissolved for every 2 hydroxides present, or that are neutralized, I'm sorry. So when you solve that, you see that basically you get 0.5 times 10 to the minus 2 molar magnesium ions, which are 1-to-1 with the magnesium hydroxide. So that is the molar solubility of the magnesium hydroxide. So once again, the acid that neutralized the base ran the solubility of the insoluble salt. And now I want to turn that molarity, the moles per 1,000 mils, into the grams per mil. So it's the same procedure, right? That's how many moles per 1,000 mils. Take it by the molecular weight. Solve. I now have 2.92 times 10 to the minus 4 grams per mils. That's my final answer. Question 3. Solve for the molar solubility in grams per mil solubility of magnesium hydroxide in 0.75 molar magnesium chloride solution. Now in this particular reaction, it's the common ion effect, and magnesium is the common ion in here that's going to mess with the equilibrium. So once again, you set up your ice table. Because it's a common ion, it goes in as the initial condition. Then you basically set up ice. Here's what happens at equilibrium, or I'm sorry, here's the initial conditions. This is what happens when due to change, and this is your equilibrium conditions. And then when you plug it in to your KSP, you plug and chug. And in this case, again, the initial concentration is so much more significant than the plus X. You can leave it out, and if that helps you figure out whether that's true or not, you can always look at the original concentration and compare it to the KSP and see that that is much greater than the 400 rule. You solve for X, which is in molarity. This is one of those you couldn't just have the shortcut. You have to work it out on an ice table. But I did simplify the math by doing this approximation. Go ahead and solve for x. This is unique because I'm trying to figure out how much magnesium hydroxide dissolves when there's already magnesium present. So this total expression of 0.75 plus x is not useful to how soluble this stuff is. You really have to work off of here. And it basically says that, look, if 2x is the hydroxide form, then x, because it's in a 2-to-1 ratio, x would actually be the amount of magnesium hydroxide that is disassociated. So in this case, this actually is the answer, all right, in molarity. And then when you go in grams per mil solubility, you basically take that number, time the molecular weight, and you have 1.53 times 10 to the minus 5 grams in every mil of magnesium hydroxide that you dissolve in a solution that already has 0.75 molar magnesium chloride in place, common ion effect. So I hope I've helped you work on these concepts with KSP and given you some good practice. So work hard.